Everyone's seen them, right? Those mesmerizing golden chandeliers that hang in quantum computing labs, looking like something ripped straight from a sci-fi movie or an alien spacecraft. They're intricate, beautiful, and absolutely futuristic. But what if I told you that this stunning, complex piece of hardware isn't the computer itself? It's actually a super freezer, an astonishing feat of engineering designed to create temperatures colder than deep space. And inside this glittering contraption, a mind-bending process unfolds, pushing the very laws of physics to their absolute limits, all to make quantum computation even remotely possible. In this video, we're going inside to unravel its secrets. I'm not talking about some fancy radiator you'd find in a high-end gaming PC or even a beefed-up industrial cooler. We're talking about a machine that, while appearing massive, chills a tiny silicon chip hundreds of times smaller than your fingernail, down to an unbelievable 0.01 Kelvin. That's just half a degree above absolute zero, the coldest temperature nature allows. To put that in perspective, it's colder than the cosmic microwave background, colder than the helium ice caps on Pluto, and yes, colder than any natural place we know of in the entire universe. And here's the kicker. It has to stay that cold 24/7 without fail. Why? Because if it warms up even a tiny bit, every qubit on that chip forgets its identity in mere microseconds, rendering it useless. How in the world do you pull heat out of something that's already 1,000 times colder than liquid nitrogen? You build a dilution refrigerator, a contraption that might look like steampunk jewelry, but runs on pure quantum trickery. It's a tiered vertical structure with multiple stages, each progressively colder as you move downward. Let's walk down this glittering chandelier, stage by stage, and watch the temperature plummet. Stage 1, why cold is the whole ballgame. At its heart, a qubit is essentially just an electric circuit, but it is so incredibly tiny that the noise from a single electron can flip its state from a 0 to a 1. When these circuits are made from materials like aluminum or niobium, they become superconducting, but only when cooled below about 1 Kelvin. Above that critical temperature, thermal jitters, imagine billions of tiny chaotic vibrations, kick the electrons around, completely collapsing the delicate quantum superposition that gives quantum computers their incredible power. Think of it like trying to balance a pencil on its tip while someone blasts a hairdryer at it. Heat is that hairdryer constantly trying to knock over your perfectly balanced pencil. The colder the circuit, the quieter the environment, and the longer that pencil stays upright. This extreme cooling is critical to prevent qubit decoherence, the loss of quantum information due to environmental disturbances. Major players like Google, IBM, and Rigetti all report coherence times that jump from mere nanoseconds at 4 Kelvin to hundreds of microseconds at 10 millikelvin. That's a staggering 3-order of magnitude leap, and it's the difference between a useless chunk of metal and a machine that can factor numbers no classical computer could ever dream of touching. So the first job of this chandelier isn't just to look pretty. It is to act as a noise-cancelling headset for nature itself, shielding the fragile quantum world from the chaos of the everyday. Without this level of cooling, qubits would rapidly decohere, making quantum computation unreliable or simply impossible. Stage 2, the warm end, 300K to 70K. At the very top of our golden structure, we're still at room temperature, around 300 Kelvin, but even here, the engineering is relentlessly precise. Copper braids, thicker than your thumb, carry crucial electrical control pulses down from the room temperature electronics. Yet these braids are meticulously stitched into stainless steel ribbons, so incredibly thin they can flex like paper. Why such an elaborate design? Any solid rod, no matter how small, would act as a heat pipe, efficiently dumping all that 300 Kelvin room heat straight into the cryostat below. Instead, hundreds of these delicate ribbons zigzag through a vacuum shroud, giving them meters of effective length inside just a few centimeters of height. This extended path drastically reduces heat conduction. The first cooling plate, typically a large gold-plated disc, is bolted to a pair of pulse tube refrigerators. These are basically high-tech, somewhat loud air conditioners that expand helium gas in precisely timed bursts. They work tirelessly to suck the temperature down to a chilly 70 Kelvin in under 6 hours. dumping about a kilowatt of heat into water-cooled heat exchangers bolted to the lab wall. That's stage 1, and it's already a significant thermal barrier. And that gold plating you see everywhere, it's not just for show, though it certainly adds to the aesthetic. Gold is an excellent reflector of infrared radiation, cutting the black body heat load, heat radiated from warmer parts of the system, by another 30%. Even the tiny screws holding things together are gold-plated, because at these extreme temperatures, every stray photon, every tiny bit of thermal energy, counts as a space heater, threatening the delicate quantum states below. The intricate wiring and numerous gold-plated components are thermally anchored at each cooling stage to prevent heat from traveling down to the quantum chip. Stage 3, the charcoal layer, 70K to 4K. Next, we descend to a crucial stage featuring a charcoal-coated heat switch. Activated charcoal, while cheap and a bit messy to handle, is absolutely perfect for this job. When cooled to 70 Kelvin, its porous structure absorbs the last stubborn nitrogen and hydrogen molecules left in the vacuum, dropping the pressure to below a trillionth of an atmosphere. Without this vital step, the remaining gas molecules would convect heat directly onto the chip, undermining all the previous cooling efforts. It's like trying to keep a vacuum flask cold with tiny air currents still swirling inside. This stage is also where we find a network of silicon-germanium thermometers, each calibrated with millikelvin precision, constantly feeding data back to the control computer. Missing even a 0.1 Kelvin temperature drift here can lead to weeks of frustrating debugging, chasing an invisible leak that's wreaking havoc on the system. This section also hosts the first superconducting coils, niobium-titanium wires that steer microwave pulses down into the dark heart of the cryostat. They're still normal conducting at 70 Kelvin, but once we drop below 9 Kelvin, they lose all electrical resistance, and the chandelier truly starts to become its own efficient electrical highway, minimizing any resistive heating that could otherwise warm the qubits. Stage 4, the helium bath, 4K to 1K. Now we meet the iconic helium-4 pot, often a large metallic cocoon-like reservoir, holding about 60 liters of liquid helium at a brisk 4 Kelvin. Copper straps, roughly the width of 2 fingers, efficiently conduct heat down from the charcoal stage above and boil off the liquid helium at a carefully controlled rate. The evaporating helium gas carries away a surprising 80 watts of heat. That's enough energy to keep a small laptop running. Yet despite this heat removal, the remaining liquid helium only warms by a few microkelvin. This 4 Kelvin stage marks the absolute limit of what conventional refrigeration techniques can achieve with helium-4. Below 1 Kelvin, something peculiar happens. Helium-4 becomes superfluid, and its heat capacity collapses dramatically. Engineers refer to this as the lambda cliff. Past this point, you can't simply pump harder or add more conventional cooling. You need a fundamentally new kind of physics to continue the descent into ultra-cold temperatures. It's here that a precisely engineered needle valve opens, allowing a tiny controlled trickle of the rare isotope helium-3 into the mix. And this, my friends, is where the real magic, the quantum trickery, truly begins. Stage 5. Mixing chamber 1K to 50 mK. Incredibly, at these ultra-low temperatures, helium-3 and helium-4 behave much like oil and water. They phase separate into 2 distinct layers. The lighter helium-3 floats on top, forming a concentrated layer. But here's the crucial twist. The heavier helium-4 is quite happy to let helium-3 atoms dissolve through its boundary, moving from the concentrated layer into the diluted layer below. And each time a helium-3 atom crosses this boundary, it absorbs energy equivalent to the latent heat of mixing. It's a constant, tiny energy transfer. By continuously pumping the diluted helium-3 out of the bottom layer, we create a powerful, continuous heat sink that can pull microwatts of power almost indefinitely. This process, central to the dilution refrigerator, extracts heat from the system, achieving temperatures as low as 10 millikelvin or less. The entire assembly for this mixing chamber is often no larger than a shot glass, meticulously machined from silver-plated copper. Why silver? Because silver-plated copper conducts heat an astonishing 500 times better than stainless steel, ensuring maximum thermal efficiency. Inside this tiny chamber, A sintered silver sponge provides an immense surface area. Think several football fields folded into a thimble-sized space, allowing every helium-3 atom ample opportunity to find a place to hide its entropy as it dissolves. In this incredible space, the temperature plummets from 1 Kelvin all the way down to 50 millikelvin, all within a space shorter than your thumb. You wouldn't feel it, of course, but if you were somehow able to stick your finger in there, the water in your cells would freeze so rapidly that the expansion would instantly shatter you like glass. It's a testament to the extreme conditions we're dealing with. Stage 6. The still 50 mK to 10 mK. Even the incredibly efficient dilution process starts to become sluggish below 50 millikelvin, so we introduce a second, even colder stage, the still. Here, a tiny electric heater gently warms the helium mixture to about 600 millikelvin, just warm enough for the helium-3 to preferentially evaporate, leaving the helium-4 behind. A quiet scroll pump then sucks this helium-3 gas up through the very center of the chandelier, recondenses it at the 4 Kelvin plate higher up, and sends it back down for another lap through the mixing chamber. Each complete cycle removes about a nanowatt of heat. That's a billionth of a joule per second, roughly the metabolic output of a single bacterium. Yet, this minuscule amount of heat removal is enough to drop the mixing chamber temperature even further, down to 10 millikelvin, and keep it there for months on end. The pump's vibrations, no matter how slight, would be catastrophic to the qubits below, so it's isolated with extreme care. It's typically mounted on a separate frame and connected to the cryostat via flexible bellows, which are often hung from the ceiling on Kevlar cords. Any movement larger than the width of an atom could easily decohere the qubits below. Researchers often joke that the most sensitive part of a quantum computer is actually the rubber bands or Kevlar cords holding it up, a humorous but accurate reflection of the painstaking vibration isolation required. The system is suspended from the ceiling to reduce mechanical vibrations, which can cause decoherence. Stage 7. The qubit stage, 10 mK, and silence. Finally, we reach the bottom plate, the ultimate destination. A palm-sized disc of oxygen-free copper polished to a mirror finish. Bolted to its underside is the quantum processor itself, a tiny silicon chip, perhaps 5 millimeters on a side, dotted with hundreds, sometimes even 1,000, microscopic crosses of aluminum. Each cross is a transmon qubit, a sophisticated superconducting island coupled to a microwave resonator, serving as the fundamental building block of the quantum computer. Every single control line, whether it's for microwave pulses, flux bias, or reading out the qubit states, passes through a series of attenuators meticulously anchored at each temperature stage. This ensures that the heat from a pulse launched at 300 Kelvin arrives at the chip, colder than the cosmic microwave background by the time it gets here. The chip itself is carefully boxed inside a superconducting aluminum shield designed to block Earth's magnetic field to an astounding part in a million. Even the screws used are made from non-magnetic phosphor bronze. Let one steel bolt sneak in, and the localized magnetic field gradients it creates would shred qubit coherence in microseconds. At this incredible 10 millikelvin, the qubits can maintain their fragile superposition for up to 300 microseconds, long enough to run 102 qubit gates, the basic operations of quantum computation. That's the finish line. This chandelier isn't just ornamentation, it's a thermal fortress, an elaborate multi-layered shield built one painstaking layer at a time, protecting the quantum chip from the chaotic warmth of the universe. If you're enjoying this deep dive into the engineering marvels of quantum computing, don't forget to tap that subscribe button. You might be wondering, couldn't we just skip all this incredible complexity and run qubits at a balmy 4 Kelvin? Some research groups are certainly trying. For instance, silicon quantum dots and certain defects in diamond can operate at around 1 Kelvin, but they often trade the need for extreme cold for an equally extreme demand for isolation. They require isotopically pure silicon or diamond grown with 99.99% carbon-12, and even then their gate fidelities, how accurately they perform operations, often lag behind those of transmon qubits. Photonic qubits, which use light, can actually work at room temperature. but they scale differently and need interferometers stable to within a nanometer, presenting their own unique set of engineering challenges. However, for superconducting circuits, the platform that giants like Google and IBM have poured billions into, and the one currently showing the most promise for building large-scale, fault-tolerant machines, 10 millikelvin is unequivocally the sweet spot. It's the temperature where their quantum properties shine brightest and their coherence times are long enough to perform meaningful computations. Until someone invents a robust qubit that genuinely laughs at thermal noise, these dilution refrigerators will continue to hang in labs worldwide, looking like metallic jellyfish, essential for the quantum revolution. Today's largest quantum chips might use around 50 watts of control power, a manageable amount. But a full-scale, error-corrected quantum machine, one capable of truly revolutionary computations, could need kilowatts just to pump the helium necessary for cooling. This presents a monumental scaling challenge, both in terms of cost and infrastructure. Thankfully, innovation is already addressing these hurdles. Startups are building advanced pulse tube hybrids that efficiently recycle precious helium-3, dramatically cutting operating costs from an estimated $30,000 per year for older systems to under $3,000. Others are exploring closed-cycle dilution units that promise to need no helium refills for 5 years or more, making them far more practical for continuous operation. While the physical size of these chandeliers might shrink from 3 meters tall to a more compact 1 meter, the fundamental physics dictates their coldness. You can't cheat entropy, you can only cleverly relocate it. The data center of the future might not just be rows of humming classical servers. It could feature an entire cryo hall filled with silent rows of golden fridges, quietly enabling the quantum computations of tomorrow, while the classical servers roar their computations next door. Spend a day or even just a few hours in one of these millikelvin labs, and you'll quickly realize it's a world unto itself. You'll likely be wearing double gloves to protect against extreme cold burns, ear protection against the hum of pumps, and a helium monitor clipped to your belt as a crucial safety measure. Why the monitor? A single liter of liquid helium expands to an astonishing 750 liters of gas, more than enough to displace all the oxygen in a typical room, creating a silent, invisible hazard. Engineers meticulously schedule helium transfers at 6 a.m., not just to beat traffic, but to avoid any subtle vibrations from heavy vehicles that could disturb the delicate experiments. They speak in terms of microns and nanowatts, the way a seasoned mechanic talks horsepower, their language reflecting the extreme precision required. Yet, despite all the meticulous planning and the technical jargon, there's an undeniable thrill. The moment the fridge hits that magical 10 millikelvin, and the qubit spectra snap sharply into focus on the monitors, the room often erupts with a quiet, collective cheer, like a sports bar after a last-second goal. Working at the edge of absolute zero is a unique blend of half-precision, half-superstition, and entirely addictive. Drop a comment below with the coldest place you've ever experienced. Mine was a bone-chilling 40-degree night in Finland, and even that feels like a sauna compared to what we just explored. Don't forget to like and share this video if you want more deep tech tours like this one. We started our journey mesmerized by a golden chandelier and ended it at the coldest spot humanity can routinely reach on Earth. Every plate, every gold-plated screw, every sliver of sintered silver exists for one singular critical purpose: to protect a handful of qubits from the relentless chaos of heat. Without this elaborate super freezer, these quantum computers would remain nothing more than complex theories on a chalkboard. But with it, they can factor numbers, simulate molecules, and one day they may just crack seemingly unbreakable encryption or design revolutionary new drugs. The next time you see a photo of that ornate metallic sculpture, remember, it's not just decoration, nor is it merely a fancy piece of lab equipment. It's a precisely engineered ladder leading down to the very edge of absolute zero, where the quantum world finally stays quiet long enough for us to harness its incredible power to compute. Thanks for coming inside the golden super freezer with me. Stay curious, stay cool, and I'll see you in the next one.